Discussion on surfaces, and we're going to specifically talk about friction. So this is our discussion on surfaces. And make sure I got an actual ink here. All right, so we're going to talk about surfaces. We're continuing our discussion, and we're talking about friction. And the goal here is I basically want to help you understand the relationship between friction and the material properties of specific surfaces. So as we know from our other coursework, when we have two surfaces that are in contact with each other, we will have a resistance to relative motion. So if we have a force here, which is our Fm, which is our mating force. Okay, so we have a force between two different surfaces. The resistance to relative motion is proportional to the actual area or real area of contact. Okay, so we'll denote that by AR. And there's a relationship between AR and the resistance to motion. And when we say the actual area, okay, we're actually talking about the actual area of the pieces between the surfaces that are actually in contact with each other. And we call these raised portions, these are called asperities in surface lingo. So these raised portions are asperities. Okay, and asperities are where the surfaces contact each other. So obviously when you apply a downward force between or a mating force between the objects, if you look and you zoom in here on these portions of the surface, let's say we're gonna zoom this out over here, we have a surface that looks like this, and we may have like these really sharp peaks. Okay, and let's say that's acted on by the other part of the surface, and we have this mating force. When this force is applied, because the area here, or the tip area of the asperity is really small. Okay, so this area is really small, often. So therefore, the stress is really, really high. Okay. So, and it's often high enough so that we get, permanent plastic deformation in the material at the asperities. We measure this. We measure the resistance of a surface to a load with, what kind of test do we use? We use hardness tests. Okay, so when we're doing a hardness test, what we're really doing is we're looking at the surface to surface interactions to try to get a feel for how hard a material is, and we actually use these hardness tests to measure what is called the penetration strength of a surface. Okay. So when we have the penetration strength, we can actually relate that to the actual area. And so the way that we do that is we take a look at the hardness test, and we basically say that the real area, okay, this is our real area of contact. We say that this is approximately equal to the mating force, or in the case of hardness test, it's just the downward force, over the penetration strength of material. Okay, and this is your downward force, and this is your penetration strength for that material. Right, so this is something that we get out of our hardness tests, and it turns out that the penetration strength is related to this variable called the real area of contact. What's interesting is that this area is also equal to about, we'll say approximately equal to, the downward force over 3 times the compressive yield strength. Okay, and so this provides a really nice way of us being able to relate the contact area, okay, with the actual material property, which is the compressive yield strength of a material. Okay, what is interesting is that the real area of contact, if you notice from this equation, right, doesn't seem to be, or isn't related to the area of the mating surfaces. Okay, and what we're talking about here is the area, or we could say, if we want to be a little bit more specific, the nominal area between the mating surfaces. Okay, so the difference is, if we just had, say, surface A, and we had, surface B, we might say, well, if we know that this object is this wide, and this object is this wide, that we can actually kind of look at this area that's between these two things, and we say, oh, well, that's the area of contact. But in reality, it's not. Okay, from a friction perspective, the real area of contact isn't related to this nominal area between the two components. That would be something that we might say right here. Okay, so that explains why, when we look at friction, why we get an equation. If we think about it, we talk about the friction force, and everybody probably remembers from physics that it's proportional to the normal force. Okay, this is our friction force. Okay, and we call this relationship, this proportionality between the friction force and the normal force. okay, we call the proportionality is the coefficient of friction. Okay, so what is kind of remarkable is that this is actually the force. Okay, so F, so I say that F is the force required to shear asperities. Okay, when we say we have to shear the asperities, what we're talking about is these. We zoomed in on a surface and we had these different peaks from different surfaces. This F is the force that's required to shear, shear off these asperities. Okay. And it turns out that this force, okay, the force that we have here, F is the friction force, but it's also the force that is going to be equal to the ultimate shear strength of the material times the real area plus any other particles and stuff that's in the way, which we call this the plow force. Okay. It turns out that that P, okay, P is usually much smaller than SUS, the ultimate shear strength of that material, times the real area. So therefore, we say P is approximately equal to 0, or approximately equal to much less than whatever this is. So therefore, we can ignore P. And then we can rewrite F, and we can just say, okay, well, F is now equal to, approximately equal to the ultimate shear times the real area of contact. But as we just saw, the the real area of contact is related to the force. So if we go back, okay, we saw that the real area of contact is approximately equal to the force over the penetration strength, which we measure in the hardness test, which is approximately equal to, for most materials, most metals, is the force over 3 times the compressive yield strength. And so what that allows us to do is take the area here and relate that to the actual downward force and the material properties. And so we can actually say that, therefore the friction force that's present is related to, this is going to be your sliding friction or Coulomb friction. We're not talking about the static friction because there's some different dynamics that occur there. This is going to be the force times the ultimate shear strength over 3 times the compressive yield strength. So that's pretty fascinating because this allows us to then say that if therefore if F, which is the compressive force, is actually our normal force, then we can say that that our friction force F, which is proportional to the normal force, we could also say, that allows us to relate the actual friction in an object to the force over the normal force, which is, in this case, F times SUS over 3 times the compressive yield strength over the normal force. And if F is the normal force, in this case it is, then we can just rewrite that the coefficient of friction is approximately equal to the ultimate shear strength of a material over 3 times the compressive yield strength of material, which is pretty fascinating. Okay, so that means that we can get a relationship for the coefficient of friction just based on material properties, and this is Coulomb friction. Or sliding friction. Okay, so this is not static friction, which will be greater than or equal to our Coulomb friction. All right. So with this in mind, and with the knowledge that, for steels, we have a relationship between the ultimate shear strength and the ultimate tensile strength. So the ultimate shear is about 80% of the ultimate tensile strength. And for other ductile metals, we can say that the ultimate shear strength is approximately equal to about 75% of the ultimate strength. That allows us to relate these all in terms of the same parameter, so we can say the yield strength. Oh, sorry, one more thing we need is if we know the yield strength in compression, okay, is between about 0.5 times the ultimate tensile strength Okay, so we're saying that the yield strength in compression is between 50% of the ultimate strength and 90% of the ultimate strength. Okay, then we can rewrite the friction coefficient. Okay, and recall that we said that mu is approximately equal to the ultimate shear strength over 3 times the compressive yield strength. Okay, so we can relate the ultimate shear strength to the ultimate strength, and then we can relate the compressive, okay, this is the Y, compressive yield to the ultimate strength, so then we can express these as a ratio of the same variables, and that allows us to say that the friction of a object is the SU, the ultimate shear minimum, over 3 times the compressive yield strength minimum for that material, which is less than or equal to the ultimate shear strength maximum over the 3 times the compressive yield strength maximum for that range of materials. And that's pretty much what the bounds are. If we rewrite this in terms of our ultimate strength, we can say that it's about 0.75 SUT over 3 times 0.9 SYC, and it's a funny looking mu, and that's less than about 80% of SUT. over 3 times 0.5 SUT, which means that mu is between about 0.28 and about 0.53, just based upon the material properties. And this value here is about the same as metals in dry air. Alright, so this allows us to relate the actual material properties to friction, which is pretty remarkable. And so if we look at the ranges of friction for different materials, we can see that the ranges of values for, and this is from your book, for mild steel, for static, the case, and the dynamic case, between 0.57. For dry, for mild steel and cast iron, it's 0.23. Mild steel and aluminum, it's about 0.47. So we see that the friction values between different surfaces are close to the theoretical values. So this is just a way of us having a means of, understanding what the mechanism of friction actually is in a material, and this relationship between the material properties as we continue our discussion about surfaces. Another thing to note is there is friction in rolling. So friction, let's get a different color here. So friction is present in rolling. It is present in rolling, but it's much smaller. It's on the order of 5 times 10 to the minus 3 and 5 times 10 to the minus 5. And this doesn't make sense, so I need to actually change the inequality here. And so we're going to correct this, and we're going to say that the friction value, okay, is less than, oops, sorry, I had the wrong thing here. Oh boy. Is greater than or equal to and greater than or equal to. Okay, so basically the friction value in rolling is really low. Alright, so that concludes our discussion of friction, and there's other surface features and failures that we need to talk about, such as adhesive wear and abrasive wear, and we'll talk about those next.